Why does a 3D printed part feel tough one way, but snap like a cracker the other way? Here's the short answer. Most 3D printing builds parts in layers, so the part behaves a bit like wood grain. Along the grain, it can be strong. Across the grain, it can split, because the bond between layers is usually weaker than the plastic within a layer. Let's put a simple picture in your head. Imagine you're making a brick wall, but every brick is a warm spaghetti strand laid down in neat lines. Inside one layer, those strands are continuous, so pulling along them is like pulling on a rope. But pulling between layers is like trying to separate two sheets of tape that didn't fully melt together. That directional strength is called anisotropy. Aniso means not equal, tropy means direction. So, the strength depends on direction. Now, why does this happen so often in common FDM printers, the ones that melt filament? When the nozzle lays down a bead, that bead is hot and soft for a moment. If the previous layer is still warm enough, the two layers can partially fuse. At the microscopic level, polymer chains from the new layer can wiggle across the boundary and tangle with chains in the older layer. That entanglement is what makes the joint strong. But here's the problem: you don't have much time. Plastic cools fast. And once it cools, the chains stop moving. That boundary turns into a cold seam, more like two stacked pancakes than one solid waffle. Under load, cracks love seams. They don't want to fight through solid material if there's a convenient fault line ready to open. And it's not just the layer boundary. Inside each layer, the printer is also laying down separate roads of plastic. If they don't squeeze together perfectly, tiny gaps and voids stay inside the part. Those voids act like little crack starters. The part may look solid from the outside, but internally it can be a bundle of fused strands with microscopic air pockets. So what decides whether layers fuse well or stay weak? Temperature is huge. If the nozzle temperature is too low, the bead doesn't melt into the layer beneath. If it's hot enough, the contact area softens and fusion improves. Cooling is the other half of the fight. Strong layer bonding likes time while hot. But printers often blast parts with a fan for clean overhangs and sharp detail. Great for looks, bad for bonding. The faster the plastic chills, the less chain mixing you get, and the easier it is for layers to peel apart. Print speed matters too. If you move fast, each bead has less time to press, flatten, and merge. Slower printing can improve contact and reduce voids. Then there's orientation, the mistake that wrecks so many functional prints. If you print a hook standing upright, the load might try to pull layers apart like pages in a book. That's the weakest direction. Print the same hook on its side, and now the load runs along continuous strands and perimeters. Same material. Same printer. Totally different strength. This is why two people can print that same part and get totally different results, because they didn't print the same direction. And this isn't only an FDM issue. Resin printing can still be directional because it cures layer by layer, and the interface between layers can be a weak plane if curing and exposure aren't tuned well. Powder bed and metal printing can also show directionality because the laser skin pattern, melt pools, and thermal stresses vary with build direction. The physics changes, but the core idea stays. Layered manufacturing often creates preferred planes where cracks want to travel. So how do you reduce anisotropy? First, orient the part so loads run along layers, not across them. If the part will be pulled, bent, or impacted, try to keep the main stress traveling through continuous paths, not through layer seams. Second, improve bonding. Hotter nozzle, warmer environment, less aggressive cooling when strength matters. An enclosure helps because it keeps the whole print warmer longer. Third, design and settings, more perimeters, better infill overlap, slightly wider extrusion, smaller layer height when it improves contact, and materials that fuse well. And finally, post-processing. Annealing some plastics can increase strength by relaxing internal stress and improving structure. Resin parts can benefit from proper post-cure. Metal parts often rely on heat treatment for final properties. Bottom line, 3D prints aren't weak. They're directional. If you respect the layers, you get surprisingly strong parts. If you ignore them, your part will fail right along the printer's built-in fault lines. What should we break down next? Why carbon fiber filament can be stronger but also more brittle, or why printed holes never come out the right size?